Hello, everyone. This is Arnava Majumdar, and we have the Cognitive Automotive Research team from NC State University here with us today. They had been working very diligently on this project for 2 semesters now. And Jeremy Edmondson, who's a professor at NC State, has been guiding them along with my colleagues at IBM, me and a few others, Ronnie Sarkar and Sudhakar as well. So we are all eagerly waiting to see the final results of this awesome project. So take it away, Cameron. Go ahead.
Sure. So I'm Cameron. I'm joined by Stephen, Byron, and Victor. And today we're going to be going over the project overview, some end-to-end system demonstration, as well as subsystem functionality, and also highlight some of the research we've been doing on the simulation using IsaacStem and machine learning. So the Cognitive Automotive Research Project, sponsored by IBM, developed a machine learning enablement platform for racing autonomous RC cars to provide a real-world training environment for engineers to acquire ML skills. Our project's main requirements were to deliver an automated deployment, cloud-based ML operations platform, and a data collection and management system. For this system, it provides a pipeline that reliably collects data from the car's sensor, stores it in the cloud so that it's accessible for developing ML models, and manages requests for ML model downloads to the race car. Some of the design challenges that we faced included reducing request latency, data integrity, and flexibility for growth. So our system architecture has a couple main components. The first is the central control, which are highlighted in the color gray. The data manager and data storage locations are in green, and the model training and evaluation are in red, which are future additions. So here is our data flow. This highlights how data will be collected from the car and transmitted throughout our system, and then also involves the model training process and redeployment back to the car. So data will be collected on the car and transmitted to the Raspberry Pi, and then to the MQTT broker, which will then go to our data polar, which is the other side of the MQTT protocol, and then will be stored in a PostgreSQL database. The images that the car collects will be uploaded to Cloud Object Storage. And when the system receives a data done message or finished uploading message in the data polar, the request router will initiate training. The model manager is going to be responsible for handling the training process. It doesn't actually do the training, but it's going to be responsible for managing everything that the system that's doing the training needs, and also to then hand it over for evaluation. Once that model has been created, the model manager will store that model in Cloud Object Storage. A human user can request that that model is downloaded to the car via one of our APIs, and the MQTT data polar will send a message back through MQTT to the on-prem system, who will then download the model from Cloud Object Storage. So we're going to quickly show an end-to-end subsystem demonstration of that data flow.
Can you pause it real quick and then slow it down? Thank you.
Yeah.
So in the beginning of this video, you'll see 2 terminal windows at the bottom. So the terminal window on the bottom left is going to represent the car sending data. It's not actually the car, it's just an emulator. And on the bottom right, it's going to be the emulator of the car receiving any data. And then the window above, the Chrome window, is going to be our logs from the systems running in the cloud. So when the video starts, you'll see the messages are going to begin sending from the sender on the bottom right. You can start the video, and they will be published, and then we can check the logs and see that the data polar is receiving the messages in the cloud. Once the transmission of the data is finished, signified by this data transmission complete message, we will then tell the request router to begin training the model. But before that, we want to ensure that the data made it to the database. So we check the database and we see that all the data that we sent made it into the database successfully without corruption. And then the request router has printed out that it had started the training. So it reached out to the model manager, and the model manager got all the data, trained a fake model, and uploaded a model into cloud object storage. We just have this TXT file right now because the machine learning part has not been integrated. So the file represents that the model has been uploaded. And then finally, the human user can, well, we're just showing here that the file was uploaded in real time. And then the human user will go to this API endpoint, and they can request that the system download the model. So they hit this endpoint, and that goes to the data manager, and they send this received message, or they send this model status ready command back to the car. So that will prompt the car to download the newly trained model from Cloud Object Storage.
So that concludes the whole entire process of data flow that we had just gone over in that previous diagram. A couple of things I'd like to point out in that video is that we're using the Mac computer to play the role of the on-prem system and to preview logs. So from the human's point of view, all of this will happen automatically at the conclusion of a race. The Windows computer in that video is playing the role of a human user and what they might want to look at. So they might want to go look at the database, or they might want to go look at what's in Cloud Object Storage. And then they also had that API that they use to trigger the download of the model when they choose to select that model. So we'll go into some of the subsystem functionalities now. First up is the data polar.
So this diagram shows just what the data polar, highlighted in red, is responsible for. So it has connections to the MQTT broker, the request router, and the data manager. So the flow would be the car would send race data to the MQTT broker, and then the data polar subscribes to those messages and will push them to the data manager to be stored. The data polar will let the request router know when the data transmission has finished to begin training the model. And then the data polar also has the functionality to send the message back to the car through the MQTT broker by publishing messages, letting them know that the model has been trained and the car can download the model. So this is highlighting the data upload process from the car, as I was mentioning through the diagram, just a different version of that. So it goes from the car to the Raspberry Pi to the MQTT broker into our data polar, which then pushes it to the database. So the MQTT message format is going to be in the same format as our database is expecting. So we're expecting that the car formats it in a specific way. We'll get to that format later on in the presentation when we get to the database design. But RabbitMQ is going to serve as the broker between the car and the data polar, and there's going to be a two-way communication. So both the car and the data polar are both publishing and subscribing messages. The one additional field of the message will be message type, and that will signify whether or not the message coming in is data or if it's the data completed message. The data polar will delete that message type before storing it in the database, and since it's already in the proper format, the data manager will be able to easily store that in the database. We'll now show a video demonstrating the specific functionality of just the data polar. So that clip right there showed that it was successfully started and connected to the broker. And we can now see that it's receiving messages. It's receiving the messages and it's sending them to the data manager to be stored in the database. We have changed this to be from single values to arrays of values. So one message from the car will be composed of several individual messages. So that would speed up the data transmission process. Now we have, oh, I guess the video got paused. I guess you can speed this up too if you want to a little bit, so it's not so long. So the way that this works is we have to expose an API endpoint. And so this is showing that the images are successfully, or sorry, the data has successfully been transmitted into the database through the data manager.
So next we'll look at the data integrity requirements that we had with the data pipeline. So I'm going to go ahead and start this video. It is fairly fast, but what I want you to see is that we're sending approximately 1,000 MQTT messages, which corresponds to 4,156 pieces of data. And what we're trying to make sure is that every single piece of data is inserted into the database without loss and without corruption. So here you can see the data puller logs that it's receiving all of these messages. And then in the database, we're watching the number of lines in the database increase. I'm going to skip to the end just because it's very repetitive. But here you can see this value in the database is what we're watching grow. And we're trying to get that to reach 4,156, because that means we didn't drop a single piece of data. And as you can see right there, we hit 4,156. The next piece of this demonstration is going to be showing that we have double checked all the lines in the database to make sure that the data that is in the database is as expected and there was no corruption of the data. So we'll compare all the values in the database against an expected value, and it will return any anomalous data. So we don't want any values returned. So first, I guess we're going to show that there's the correct number of lines, which we showed there. And then finally, we'll look for any anomalous data and we get 0. So that means that all the data was inserted into the database without loss and without corruption. So we have ensured the integrity of the data pipeline from the car all the way through to the database. So next is the data manager. So the role of the data manager is to provide an abstraction to the rest of the pipeline and ML ops systems of where the data is actually being stored. So it doesn't have to manage different types of APIs. It just has to worry about the one for the data manager. So we are having the data manager communicate with both the Postgres SQL database running on the IBM Cloud and the Cloud Object Storage. The Cloud Object Storage is used for images and for models, and the Postgres SQL is used for the data collected, any numerical data that we collect, like what we just showed with the car. So this video is going to demonstrate first that we can retrieve an image from the Cloud Object Storage. So that's the most recent one. So we were able to receive that. And then here we're showing that we can retrieve a list of the images that are within Cloud Object Storage. So that way we don't need to know the file names before we want to go retrieve an image. So we can run this, pick out an image, and then go and retrieve that image. And then the last piece is here. This is the API for inserting data. We got a 200 OK. And then finally, for retrieving data, we can get a list of all the data and all the values that are in the database by using that API. Up next is data storage. So I think I briefly had gone into what type of data was stored in both, but we'll go into some more information now.
So we have a very rudimentary database design. Right now, we just have the ability to store team ID and device ID, and then a couple of sensors, the different IMU sensors, and then wheel speed and steering angle. We also take a couple other metrics such as the date and the time and the run number. This is mainly for one car and one team. That was the assumption that we were operating under when we were making our system. Obviously, this is not scalable, and we knew this was not going to be scalable. We did work with Ron, and he introduced some more scalable database designs, but due to the scope of our project, we did not have time to implement that 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 complex of a database. So this is a very simple one, and it works for our methods with one car and one team.
So for cloud object storage, again, we took the assumption of one team, one car, and we created a hierarchy of how the information was going to be stored. So we assumed that a bucket was for one team and it was going to hold all of the image data, and that within that bucket, we would have prefixes for each of the runs that the car did. And then the second level was going to reiterate that prefix name just as a extra failsafe, and then provide the timestamp that the image was taken. This helps preserve the time series nature of the data without having an additional component that will make things harder later to put the images back in series. So we can look at the file names in order to determine the order that they were taken in. And so this will allow us also for things to be searchable based upon a run, and provides a fairly easy way to name the files on the car side as well. So up next is the request router. The request router is kind of acting as the centralized location for all of the traffic going in and out of the system, other than the MQTT. So the request router is really where the evolution of the front end UI will go into, and it will handle pushing requests to where they need to go. So when the human user does a request to publish the model to the car, the request router will be the one that initially receives that, and it knows to go talk to the data puller to publish a message on the MQTT back to the car. It can also go to the data manager to retrieve information that might be of use to the human user or to other requests. And then it can also go to the model manager for the training. So here we'll see demos of the connection of the request router first to the model or the data manager. And here we're going to get a list of images which might be of use to a human, just wanting to know what images they have available for a model. Here is the model manager and the request router communicating. Here it's for a request to start training the model, and the request to start training the model right now returns an image as if it had gone to get data for training the model. And then finally, the data puller and the request router. This is for downloading the model back to the car. And you can see here that that returned an MQTT message back on the listener for that would play the role of the on-prem system. Up next is the model manager.
So the model manager, highlighted in red, can be kind of thought of as the central operating system or brains behind the model training process. So it has connections to many things in our system, but primarily it's going to be communicating with the data manager to get data, and then passing the data to the various training environments that we have and evaluating the models, and then putting the model back into cloud object storage if it is deemed to be more effective than the previously trained one. So the next video that we have here is a demo of a couple of things that the main thing that the model manager does right now. So we're going to hit an endpoint to begin the model training process. So what you see is you see an image returned. This is just to prove that the model manager went and communicated with the data manager, and then we have the uploaded model into cloud object storage. So as we've kind of alluded to before, we have yet to implement the machine learning portion into our system, but with the model manager, we have shown that it has the functionality to get the data and pass the data around to where it's needed. And it can also upload models and files to the cloud object storage So once we have agreed upon the types of machine learning that we're going to use and the environments, it's easily able to plug into the model manager and take advantage of all the functionality that our system provides.
So up next, we'll talk about the cloud deployment automation. So for each subsystem, we have a script that will clean and package the code, create the necessary build config and image streams, upload the files and start building the images, create the root services and deployments, and then also modify environment variables to have correct routes or other things that can only be determined at runtime. So this script works where a human user only has to input 2 commands in order for this script to work. Here, I'm just showing that none of the code is pre-compiled and that there is currently a clean workspace in OpenShift. So there's no extra requirements about how this needs to be set up before this can work. So I'm going to pause here for just a second because I know that went really fast. So I want to point out the 2 commands that were used. This first one is a login command because you need to point the OC command line to where you are running and authenticate. And then the next command was just the deployment.bat, which is the automation file. So once you run the automation, everything is taken care of. So here it will start kicking off compiling code, building the images, uploading them, doing all of the steps that I previously mentioned. And this is going to go through and do it for every single component: the broker, the data puller, the data manager, the model manager, the request router. So you can see here that I was able to create all the resources, and here the builds are still running. This is pretty typical after the script is that the builds are still running after the completion, and that's perfectly okay. Everything will still work. And so eventually you'll get those images in the image stream. And then the routes and services are all handled. I'll go back there to the end because I know that's really fast. And then you can see at the very end here that, oops, I keep missing it, that all of the deployments are successfully up and running, and there was no extra steps needed by the human user to get these services up and running. What that command and OpenShift took care of everything. So next, we'll hand it over to Byron to talk about his research on Isaacson.
So a straight goal of mine for the end of the semester was to develop Isaacson in a container for the cloud structure. And I wanted to point out that in my research, trying to set this up, I found out that you need a Linux workstation, and I was using a Windows workstation. But the next couple of slides highlight the commands that you were to type in if it was a Linux system. So at the top, at the bottom, you can see that where it links to the GitHub repositories for headless mode. And then on the next slide, you can see that the command to check your GPU and pull the container, for Isaacson. And then on the next slide, I was trying to demonstrate the communication between Isaac and the local host that I set up through Omniverse. And I defined a simple function at the top called ping, and then just a simple response, pong, to coincide. And then there was an extension on the next slide that I only had to change one line to do so. And then if you look at the next slide, you will see this is the local host screen that I set up through Omniverse for the local workstation I had running Isaacson at the campus. And you can see where it logs on, has the request, it responds with the word pong, showing the successful communication once I hit execute. And then so this was just a little quick video showing the work that I did in command prompt and trying to incorporate the Isaac Gem and machine learning features over to be used by Isaac Sim. I didn't quite get it finished, but there was I was able to successfully download a lot of the packages and just have run out of time to finish the rest. And then if you look at the next slide, get in here. Can you go to the next slide? This is just a simple example. There's a lot of support through NVIDIA for the JetBot example. And this is kind of just showcasing the OmniGraph features. It's set up kind of like LabVIEW, where you have separate modules and you just link them together with wires, and each one control a different aspect of the asset. And then the next slide's video. I was trying to do the same thing with the Jet Racer asset because that's the actual car we'll be using. And when I linked all of the items up, you can see it kind of just explodes off into the universe. But it has a nice camera view. And then if you go to the next slide, that'll be it.
So in terms of machine learning, some updates from last time in terms of the lane detection model. I have sent Ronnie the pipeline I used, or just all of my data pre-processing, training, and predicting. I don't know if he told you about that, Ron, but I share the folder and the data set with him, so hopefully he can take a look at it. But something else I changed, because I had an interesting problem where it was a little too time intensive for me to very accurately label the lanes. So instead, what I did, which is usually a very hard thing to do in machine learning, I don't know if you guys have ever done computer vision, but usually when you train a model, you need hundreds, even thousands of pictures. And I trained this model with only 50 pictures. But what I did instead was, if you can see here, this is part of the data augmentation where I used coarse dropout, which is so just imagine you have an image and then you have the holes. They are 45 by 45 pixels, and they just black out the image, but then the Y label is still the same. So the model can learn to kind of fill in the blanks, Gaussian blur, just adding noise, channel shuffle up the RGB values, and then combinations of those as well. And so from that, I created 12 images from one image. And so that is a something that hopefully next semester's team, they can gather more data and label it, and then just use my methodology, because it worked well enough with only 50 images. I think it got good results. Okay, you can go to the next one. And so here's an example. In the above, this is the above is a validation slash test, or I believe it's the test image. So it's something the model had never seen before. You can see it has decent results. And then the below is from the Donkey Sim racetrack. And so the reason I tested on the Donkey Sim is because I just wanted to make sure that the model could extrapolate well enough that when I put it, or I didn't I couldn't get around to slapping it on top of the RL model in the Donkey Sim, but I hope next semester's team could. I just wanted to make sure that it could extrapolate and it would be useful in the Donkey Sim simulator, which it looks like it does work, and it it gives realistic results. And then here is the general way that the Donkey Sim works. And the big thing to notice here is the CNN for the lane detection, which is the Deep Lab V3 Plus model that I have created. And so that is something that the whole reason I'm doing this is because imagine you take a picture of the road. There's just so much noise in there. If you can get rid of all that noise and have it just be the the two lanes as close as they are to you in the angles, I think it would give much quicker and more accurate results, especially when going from simulation to reality, because there is a big gap. You can go to the next one. And so here is just a video of me doing a donkey sim tutorial. You can see in the left, I did it with using stable baselines 3, the PPO model, and it has a CNN policy, which is just the okay, CNN neural network. It's not a lane detection, but segments the image somehow, and it takes random steps. And as you can see, this was trained on the CPU, which is no good at all. Never do machine learning on a CPU. It takes 50 plus times as long as a GPU. So here you can see machine learning does something very interesting in the beginning, where it does like a random walk to try to see where it gets better results. And here it's having some really strange behaviors. You'll see in the next video, I improve the results, or at least the visualization of the training by there's this parameter in the simulator which is like the simulated time, or so you can speed up the simulation. So the last one was just the regular time, and this one's like times 50. So you can see as it goes through all the different runs, it's very choppy. It's on the CPU. It's no good. I probably did it too fast, but so you can see it. What happens here is it goes through all these iterations. It will just keep doing random things, updating the policy, and if it goes off the track, then it restarts the what's called the environment. And you'll see at the end some weird behavior occurs, or it's very choppy here. It's 1 FPS. It's no good. Definitely have to do this on the GPU, especially because the lane detection model I made is 4 gigabytes, so there was no way. There's no way. So you can see here, it keeps getting stuck in the same action for some reason. It's not just stuck there, it's like turning right for some reason, because it's so choppy. And go to the next one. I think that's it for me.
So we can go through some of the material, or you can kind of choose what you would like us to show next. But I would like to highlight in our product requirements document, we have documented all of the requirements and all of the successful test cases. We didn't have any failing test cases, which is excellent. And for every test case, we have linked either a photo or a video showing the success of the test. Just close that one. And then we have gone ahead and pushed all the code for the cloud to your repository. It is under cog and then cloud. And then this is all of the code that we were running in those demos.
So that's good. Is it on a separate branch or it's on the main branch?
It is on its own branch. I didn't.
Yeah, that's what it looked like, right? Okay.
Yeah.
Yeah, that's fine. I'll merge it in later on. So thanks for pushing it in. And I'm assuming all the documentation stuff that you were doing is on Box.
Not yet. We're gonna have that done for our closure meeting on Tuesday.
Okay.
Currently, it's still in Google Drive. So, is that
Okay,
something
that's fine. Yeah. So yeah. Yeah, so just make sure that you're not missing anything as you close down the semester and graduate, so we don't miss anything. And some of you might be working on this during summer, so that'll be great to have you guys. Okay. So this is really nice, team. This is a lot of work, and I'm glad we got to this point by the end of this semester. I'm sure there's a lot of things to be done, especially on the modeling side, on the simulation side. But at least the framework is in place for data to be transferred over to the cloud and back. The MQTT protocols are working and all that. I didn't see one thing mentioned in the slide. I saw Raspberry Pi, but I didn't see the logo, or maybe I missed it, for NVIDIA. We're actually using NVIDIA Jets and Nanos on the car, which is another team who's actually looking into that. But just to mention that, yeah, that car actually has Jetson Nano, where we'll run the models. So yes, and as Victor mentioned, running any sort of ML/DL model on CPUs is very slow, and GPUs obviously can break it down into thousands of threads. And yeah, though Jetson Nanos are not very strong, but I don't think we've reached that limit yet. But at some point, we'll probably have to upgrade and go to the next model. But this is great work. And thanks for pushing all the pieces onto the cloud, the OpenShift environment, and getting it all done in a timely manner. Thank you so much, team.
Thank you.
Thank you.
Jeremy, any comments as we close this meeting?
No, I think there's been some excellent work that's happened here on the part of the team, and some really good mentoring that's happened, Ron, through you and your team. So thank you all so much for that.
Thank you so much, Jeremy, and thanks for supporting the team throughout the 2 semesters. So thanks everyone. Thanks Cameron, Steve, Byron, Victor. Thanks for participating, and thanks for all your contributions. And hopefully we'll meet again and work on this or some other project in the future. And I will be issuing all your badges, and do accept it and share it on LinkedIn and any other social media platforms you wish to. So congratulations for completing the project and earning the badges.
Thank you.
I'll be in Boston, but let me know if you'd like support on the part I did with the ML. If you are working with those people in India, I believe is what you were saying.
Yes.
I'll be remote.
Yes, and we will be collaborating with Elite College in Shodhpur, which is pretty close to Kolkata, about 2 hours from Kolkata. So we will be working with those students and the professors there, and enhancing this. And we will carry on with this project during summer as much as we can, and mainly in the next semester in fall with NC State University. So a lot of promising things to be done in this project, and eventually the goal is to have it as a competition at some point, when we have all the pieces together and we're at a fairly reasonable position to open this up for competitions.
Sounds good. Thank you.
Okay, thank you so much. Thanks, everyone.
Thank
Thanks,
you.
everyone. Have a great day. Bye.
Bye.